So let me show you by looking at one simple example. And you can see that basically all the examples, all the problems you solved or you are going to solve are basically fake. Okay? You encountered multiples of this problem. You have two current conducting wires fixed in space, right? But now that you know, once they both conduct current, each one is going to exert force on the other. Okay? Let me write out I times dl cross b, right? You have to perform closed loop integration. Let us determine the direction of the force first. Wire number 2 carries a current of I2, right? Using your right-hand rule, what direction is its magnetic field acting on wire number 1, right? Your thumb is pointing in the direction of the current. Therefore, you have self-closed magnetic field lines, right, in this direction. So at this location, the B is into your eyes, okay? At this location, B21 is into your eyes. So DL cross B, DL1 cross B, you have force 2-1. So the second current conducting wire is trying to pull the first wire towards it. Okay? At the same time, the first wire is also having the current going upwards, and therefore you use your right-hand rule, right? The thumb points in the direction of the current, so your magnetic field lines are circulating in this way. So at this wire, B12 is pointing into the paper, right? Into the paper. So the force experienced by the second wire due to the field created by the first wire, DL in the Z direction, making a cross into the paper, is pointing to the left, right? So this is F12. This is showing you the force, acting force, counteracting force, are having equivalent amplitude but reversed in sign or in direction. Okay? So after this analysis, just tell me, can you really have two current conducting wires sitting in space, well behaved, without ever changing their location value? It's impossible, right? You have forces. You produce forces that tend to pull each other together, closer and closer. Okay? All right. And this is coming from Ampere's circuital law. So the numerical derivation is very simple. I'll just leave that to you. But what I'm telling you is, in the real world, there is no stationary loops or wires. Okay? They tend to move. So they can be there unless you have some kind of things to fix them. Okay? You need to fix them in space. Otherwise, they get pulled together. All right? Very last PowerPoint slide. And we end magnetism. I know you don't like magnetic fields. I see no objection from the students. You don't like magnetic fields. Okay. In any case, in space, if we have magnetic fields or flux densities, we can always decompose the flux density into two contributions, depending on your loop geometry or location. It's relative, okay? You can always decompose. So in this case, you have a current conducting loop positioned in this way. It's circular. So the surface area is now on the paper, right? So the surface normal is pointing into your eyes. Then in space, you have some B field distribution. Then you can say, oh, all the B fields perpendicular to the surface is called the perpendicular contribution, right? Now you can also have the fields that is parallel to your contribution, to your surface. That's fine, right? So right now, we have defined our loop. This is placed on the screen. So when it's on the screen, all the fields perpendicular to the area is called the perpendicular component. All the components that's on the paper is called the parallel component. So it's a relative definition. But can you please use this force definition? Try to work out on your own and tell me which field component is going to expand your loop and which field component likes to rotate your loop. This is called the perpendicular field, right? All the fields are into the paper, making a perpendicular crossing with the surface encompassed by the loop, right? So everywhere, every differential length on it, I know I have a clockwise current. So therefore, the DL is also counterclockwise. So in this case, DL cross B, right? For this particular segment, I have a force going upwards. If I evaluate this differential length, DL cross B, the force is going downwards. So if you analyze every location on this loop, you will see that each segment is going to experience a force that tends to expand it. Okay? Meaning, if initially you have a weird looking loop and you have current conducted, right? Under the presence of the B fields, and your wires are very soft, after you position that type of wire into the space, after some time, the wire would look like this. Right? It will be expanded to its maximum allowed geometry. And once you have a force circle, all the forces would tend to cancel out, right? So you ask yourselves, after that weird looking loop is expanded into this perfect circle, what is the net force? 0, right? This one is canceled out by this one. This one is canceled out by this one. So it reaches steady state. The net force is 0. Okay. So basically, the perpendicular field contribution can be used to expand your loop. On the other hand, the same current conducting loop with the presence of B field parallel to the surface, you can still use the force calculation, right? On the top, you have DL cross B. So your force is going into your eyes on the top. On the bottom, DL cross B, DL cross B. So your thumb is pointing into the paper. So basically, this is telling you this parallel field is somehow dividing your loop into halves. The top part will experience force coming out of the paper. The bottom half would experience a force into the paper. So what does that mean? That means it will rotate, right? Rotate using this center diameter, right? So it will rotate. So the top part is having a force coming out. The bottom part is experiencing force going down. So it rotates this loop. And that generates a torque. So the torque, due to parallel magnetic field, is quantified as the magnetic dipole moment of your current conducting loop, making a cross product with your external B field. You can check. M, in this case, M is into the paper, right? Your current is flowing in the clockwise direction, so M is into the paper. M cross B, yeah. So basically you have a rotation. Okay? So this torque follows this direction, right? Coming out and in, so it's rotating in a three-dimensional way. Okay? And that's your torque. So the world of magnetism is mathematically it's more difficult to solve, but in terms of the motions it can create, it is richer as compared to electrics, right? So I'm trying my best to attract you to the world of magnetism. Eventually I might fail. I think I failed again, sixth time. But I mean, you will enjoy it as you write the homeworks and on your final examination. So in the end, you will love magnetism, okay?